All right, hello once again. This is Jeff Scott of Rankin Technical College, and I've been going over the PowerPoint presentations for Tony Gaddis's Starting Out with Java Early Objects 5th edition. And as mentioned in the last video, I'm doing these a little out of order. I've done the first 12, and I'm going to go through chapter 15 next because chapter 15 is about the shortest chapter in the book. All right. It's on recursion and it only has around 20 PowerPoint slides. So we're introduced to recursion. We talk about solving problems with recursion. We give some examples of recursive methods. We talk about a recursive binary search method. Excuse me. And then we finally end the chapter by talking about the towers of Hanoi. All right? So when we talk about recursion, and what I'm about to show you, I don't remember because I haven't looked at the slides for a bit. But so what I'm going to show you may be repetitive and it may be shown a little bit later in here, but that's okay. All right. I'm not sure if you've ever heard, the two things that are used most often with recursion, I'm going to show you right now. All right? And the first one is something that's referred to as factorials. So if I say 10 factorial is equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what it actually is equal to. Okay? That's a big number. I don't know what it is. I've never tried to figure it out. But really, when you think about it, what 10 factorial is also equal to is it's equal to 10 times 9 factorial. And 9 factorial is equal to 9 times 8 factorial. And 8 factorial is equal to 8 times 7 factorial. You get the idea. I'll put my infamous ... here. All right. And 1 factorial is actually equal to 1 times 0 factorial. And 0 factorial is just 1. So we don't put a 0 there. But the point is, what this shows are a couple of the hallmarks of using factorials. I'm sorry, a couple of the hallmarks of using recursion. One of the hallmarks is you've got to have a problem that you can apply a method or an algorithm to where the problem gets easier every time you apply it. And that's what's happening here. So this time we have 10 numbers. The next time, we're having 10 times 9 numbers, and then etc. So you can see what's going on here, okay? The other thing when you work with factorials is you can never, try that again, I'm sorry. When you work with recursion, you must have an algorithm that eventually ends. So you can't have an infinite recursion type of an operation. If you were to do that, what would happen is eventually the program would start sucking up all of your system resources and it would, for lack of better words, take over the computer. Now the other time, so that's factorials, but the other time where you quite often see the use of recursion, all right, is in Fibonacci numbers. I'll leave it there. So the Fibonacci numbers go like this. If I take 1 and add 1 to it, so 1 plus 1, I get 2. 1 plus 2, I get 3. 2 plus 3, I get 5. You see the pattern and the progression here. This is another example. Now, any program that you solve using a recursive algorithm can also be solved non-recursively. Some people totally steer clear of using recursion because recursion can be a real hog of system resources. All right, and they don't like it. Some people just find the actual way that you set up algorithms recursively to just be, they don't like them and they don't use them. I want to check and see. Okay. I'm hoping that while I'm giving this presentation, this is the Chapter 12 production. I'm hoping that that stops so that I am able to finish that up. Okay. So, as mentioned here, we've been calling other methods from within a method. Recursion is the act of a method calling itself. A method that calls itself is a recursive method. Now, the example that they show here, and they won't show it on the slides, but that's shown in the book, that endless recursion does not ever end. Again, you don't want that to happen. Every time when you run a recursive algorithm and the program method calls itself, what it has to do is for each time it calls itself, it has to grab all of its values and everything else, all of its, it kind of takes a snapshot of itself, for lack of better words. And it's got to put all that information on the stack. And every time it gets done with that, it's got to unwind the stack and bring it back out again. So the example that's in here, this endless recursion, displays the string, this is a recursive method, then it calls itself again. Because it's repeated endlessly, all right, it would be an infinite loop. So you can write an infinite loop with recursion just like you can write an infinite loop non-recursively. So as mentioned in this third bullet here, a recursive method must have some way to control the number of times it repeats. Typically when people write recursive methods, they write the recursive method because it can result in much less code. That doesn't mean that it's going to execute faster. It may execute actually slower, all right? But if time is not of the essence, so if I was writing a payroll program, and let's say that every other Tuesday or every other Friday I ran the payroll program, and I had 10,000 employees, if I write it recursively, maybe it takes 15 minutes to run the program, whereas if I do it non-recursively, it takes 10 minutes. But if I have half the code, it may be worth my while, or at least I may think it's worth my while to write it recursively. And for something like a payroll program, 5 minutes isn't going to matter one way or the other. I'm going to continue to keep checking here. Okay, it's about half done. So as it says, in this example here, the method is first called from the main method, and the second through the sixth time, they're called recursively. So this is called from outside of the method the first time. The other ones are called by the method itself. So recursion, again, is the method calling itself. All right? Most of the stuff on this slide I've already gone over with you. Recursion can be a powerful way to solve repetitive problems, but it's never required. Meaning that any problem that can be solved recursively can be resolved non-recursively. Typically, as it says, by doing it iteratively within a loop. And as I also mentioned previously, in many cases, recursive algorithms will actually be less efficient, meaning they'll run slower. This is the same kind of an idea that I mentioned to you before. Recursive solutions must repetitively, so each time, allocate memory for parameters and local variables and store those addresses. This is referred to as overhead, and again, it takes place within each method call. You don't get this kind of overhead within a loop. Some repetitive problems, as mentioned at the bottom here, are more easily solved with recursion than with iteration, but virtually always an iterative algorithm is going to execute faster, while a recursive algorithm may be up and running faster, and it may result in less code. So here's kind of the magic of it. With recursion, you establish a base case. So you need a start. If that base case is matched, the method solves it, and the idea is it gets a little bit easier every time. that you run it. All right? So earlier we talked about an example of a selection sort. So let's say, and remember, we're talking here about the computer, not about you or me. So let's say that we had 10 numbers. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and what we want to do is we want to have a selection sort. With a selection sort, what happens is we go through this list, and the first time through, we find the smallest number, which is -34, and we move it to the top. All right? Now, we could do this recursively because we've got 10 numbers here that we're sorting, but after we do it the first time, now we only have 9 that we're sorting. So the problem is getting easier every time. And as you can see, you know, it's what you think. We go to 0, then we'd only have 8 to go through, so we'd get 11, then we'd only have 7 to go through, and it looks like we go to 34, so we'd have 6 to go through, 56, we'd have 5 to go through, 67, we'd have 4 to go through, 89, we'd have 3 to go through, 212, we'd have 2 to go through. 765, we'd have 1 to go through. And 888. So you can see this is not a hard algorithm to solve non-recursively, but solving it recursively could result in less code. Typically, that's why developers will use recursive algorithms, because it results in less code. So again, if time is not of the essence, and if it's a problem that you can solve by coming up with a base case and then making it easier every time, and if the problem eventually is solved, in other words, it's not infinite, all right, recursion can be a good solution, okay? And that's what they're saying here. Base case, if matched, you solve it and you return. If the base case can't be solved now, you reduce it to a smaller problem. All right? In mathematics, as you know, then they're talking about factorials. So I'm not going to sit there and go over this one with you because I already did. So really, this is backwards. Really, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 times 0 factorial, which is 1. So the base case, as it says, is where n is equal to 0. So that's when you know basically you've got to have a way to stop this, is what they're saying. So kind of nice. Now, I'm going to grab the example that they have here, because it does demonstrate something that at least I think is important. You may or may not agree. But I'm going to come in here. I don't need that anymore. I'm going to put in this, because this is what they show in the book. And it's totally correct. Okay? But you really start to see, in my opinion, why it's a good idea to use curly braces here. Because if we look at this example that I'm writing right now, again, in my humble opinion right here, let's make this a lot smaller, because I think you can read it even if it's small. All right, in my opinion, when you look at this, and you look at the example that I just put in here, this example, that sure is much easier to look at and figure it out as opposed to what the author has put here. There is nothing wrong at all with what the author put there. It's totally legitimate, but it's much harder to read. All right, so they give you a Java-based solution. And actually, this solution would work in virtually any kind of programming language. It would not have to be done in Java. But as this is a Java book, that's why they're showing it that way. So here they're showing it with recursion. Okay? You can have both direct and indirect recursion, and as mentioned there with recursive methods, when they directly call themselves, it's direct recursion. So if A calls B, which in turn calls A, but you can have A which calls B, which calls C, which calls A, and that's indirect recursion. You've got to be very careful when you write different recursive algorithms because it's very easy to nest yourself and put in something that's wrong and get yourself into an infinite loop type of condition. Here's another example where you can use recursion to sum a range of elements. Okay. So what this is basically saying is if you've reached the end, return. All right. So this says if start is greater than end. So basically this would right there would well, let's see. If start is greater than end, return 0. I think that's if you had an error condition. Otherwise, you're going to return this. What this is going to do is it's going to add 1 plus 2 plus 3 plus 4 plus 5 plus etc. All right? But in this case, I'm wrong. What they're doing is they're saying range sum. So they want to add element 3, all right, and they want to add, I think, the next 7. This is probably element 3 through the element 7. So 0, 1, 2, 3, 4, 5, 6, 7. So this will add this 4 plus 5 plus 6 plus 7. 3, 0, 1, 2, 3, 4, 5, 6, 7. So this will add 4 through 8. All right. And sometimes people look at this and they say, okay, I even get this. But it doesn't seem in this case like there's a big difference in the amount of code that you'd write, so why write it recursively? And a lot of people feel that way. Here's another example. Good, that finished. Here is another example, and in this example, they're drawing concentric circles. What this would do would be almost like the old spirograph toy that you might have seen when you were a kid, or maybe not, where you can draw a bunch of circles. I mentioned Fibonacci to you also. I guess I didn't put the 0 at the beginning, which really should have been there. All right. But every time you add 2 numbers up, you get the next number. Add 2, you get the next number. Add 2, you get the next number, etc. This is used to predict a lot of different things. One of the things that it's used for is with rabbits, to predict if 2 rabbits mate and then those 2 rabbits, they have a child or children, and those 2 mate, etc. How long it would take till you get to a certain number. So here's an example of solving it with recursion. This method has 2 base cases, and again, with that base case, what you're saying is if you reach a certain point in here, you get out. All right? And they give an example of it in here also. This is the greatest common divisor, or GCD method. So if I have 2 numbers, for example, I have 24 and 12. What's the biggest number that goes into both those? And the number is 12. A type of an idea. Binary search, recursive binary search. And they're showing another one that you could do. The Towers of Hanoi, if you've never seen this, they have a picture of it in the book. As it says, you've got 3 pegs and a set of discs with holes in their center, and the idea is moving everything over from, I think, the beginning peg to the ending peg. You can only move 1 disc at a time. A disc cannot be placed on top of a smaller disc. All discs must be stored on a peg while being moved, etc. So they show how this can be done. It's kind of a classic, for lack of better words. So that is it for this chapter. So we've got another chapter out of the way. And as mentioned previously, we have 3 chapters left. The next chapter that I go through will be chapter 13, which will be on applets. And I'll talk about applets, but they'll make more sense, I believe, when we have the lecture on applets. Then we'll go into chapter 14, which shows another way of doing GUIs with JavaFX, which is fairly new, but I've never done anything with it, but I will lecture on it. And then chapter 16, which is on databases. And I do want you to understand that there may be chapters when I go through writing some programs, there may be some chapters where I write more than one program. It's also not inconceivable that there may be a chapter or two for which I write no program. All right? So I'll be back later with the next PowerPoint presentation.